Hey, good morning, everyone. Can y'all hear me okay? I'm coming through loud and clear, hopefully. All right. Well, hopefully you got outside and enjoyed the day a little bit yesterday. Actually doesn't look too bad outside again this morning. So anyway, hopefully you can get out and do some lunch, walking, or at least not stare at the computer. You can limit your staring at the computer to what's necessary for class. But anyway, so I guess the big thing today, or one of the big things today, is that homework number one is due this afternoon at 1 o'clock or 12:30 or whenever you want to submit it. I've gotten a couple of them from you. So let's start here by just asking, did anybody come up with questions or other things that they wanted to talk about um, before we have to turn it in here this afternoon? Any questions about anything? While you're thinking, I did want to share with you that I think some of you caught that there was a typo in the homework. Hold on one second. I got to find it. Okay, so you caught that there was a typo in the homework. It was in question number 6, I believe, right? So it says, now download the data on real private investment, identify whether, some reason I put unemployment here. I meant to write investment is pro-cyclical, counter-cyclical, or acyclical. I think most of you figured out that that was a typo. A couple of you sent me emails, and hopefully we got it straight, but I just wanted to alert you to that. I'm sorry about that. As hard as I try, I always have a typo in one of these things somewhere. I don't know why it's impossible for me to prevent that. But anyway, but I think most of you caught it, right? Or at least reached out and asked me what was going on. So anyway, I apologize for that. Are there any other questions about the homework? A few of you showed up to office hours yesterday afternoon and had a couple of reasonable questions, but in general, things seem to be going pretty well. So, okay. So this afternoon, I'm going to share you your second homework. Okay. So after class this afternoon, I'll show you your second homework. Your second homework is going to be on chapters 4, 5, and 6. So basically what we talked about yesterday, what we talk about today, and what we talk about tomorrow. And your second homework, I believe, is going to be due Monday afternoon. So you'll have the weekend to work over it. And so yeah, so the plan is for you to get that to me on Monday, so I can get you back your homework on Tuesday, so that you have both homeworks number 1 and number 2 ready to go to help you get ready for the exam, the first exam, which is on Wednesday. And we'll have a little bit more to say about the first exam come the beginning of the week. But anyway, that's just so you kind of, that. I think actually this whole schedule is on your syllabus about where homeworks are due. So just so you know. And so I would highly encourage you once again to spend a little bit of time working on homework number 2 tonight. If for no other reason that you can ask me some questions on Friday. There'll also be some opportunity. I'll be responding to questions over the weekend, but if you want to ask me some questions tomorrow before the weekend, that would be a good time to do it. So, all right. So any other questions about anything, or you just want to jump into this? Okay, let's go. Let's go. So we're going to talk about the solo model today. Okay. So if you remember, just a step back, what have we been doing here the last couple of days? Well, yesterday and today and tomorrow, we're really trying to develop a theory of economic growth, a theory that helps us understand why economies grow over time, what are the important factors that drive growth, why some countries grow and other countries don't grow, why some countries have high standards of living and other countries don't have high standards of living. So the first step of this was what we did yesterday in chapter 4, a simple model of production. And it was a simple model, right? It was a simple model. And one of the things that made it simple was that we did not have time as an element in the model, right? So it was a static model. Time did not change, right? So that model was very much like a snapshot, right? Where you're taking a picture, kind of explaining where a country is today, but not really able to explain where growth comes from and how economies evolve over time. And so that's really what we want to talk about today is, can we take that simple model that we talked about yesterday and make it dynamic? And by dynamic, meaning can we add the element of time to the model so that we can begin to think about how growth happens and how economies evolve over time? Right, so what we did yesterday was really talking about income levels. Today we want to talk about income levels, but also growth rates. And so the model that we're going to use is a model that was developed in 1956 by an economist by the name of Robert Solow. Right now referred to it as the Solow model. Solow's paper in 1956 was very humbly called A Contribution to the Theory of Economic Growth, right? And it's probably one of the most cited papers of the 20th century, right? And this, among some other things, was won Robert Solow a Nobel Prize. And so one of the reasons why the Solow model is so widely used among economists, and so even today, right, even 70 years after the model was developed, it's still so widely used by economists, is you're going to see that it's really surprisingly simple, right? It's really surprisingly simple. And so that's always what makes a best model, right? A model that is simple, but also has some very important insights into why different countries grow at different rates. And so, so let's jump into it and talk about what the Solow model is. Okay, so just like we did yesterday, right? When we talk about a model, we really have to begin with the model's assumptions. All right. So what are the assumptions of the Solow model? First off, we're going to use the same Cobb-Douglas production function that we used yesterday. A couple of small differences here, though. Okay. A couple of small differences here. That's 1/3. Kind of looks like a 2. Okay. A couple of small differences. Note here that we're going to include time in our production function now. So these variables have basically a time subscript to denote that they change over time. So output's going to change over time, A is going to change over time, K is going to change over time, L is going to change over time. Just like yesterday, this production function exhibits constant returns to scale. If you double capital and you double labor, then output will double. Yesterday, we assumed that capital and labor were fixed, but now we are not going to fix capital. So while A is fixed, or what we can say exogenous, just like we talked about yesterday, we are not going to assume that capital and labor are fixed, at least not right now. Okay, so we're really beginning with the same fundamental model that we talked about yesterday. The big difference here is time. Right now, we're going to try to incorporate time into this. The second assumption, pretty straightforward. is aggregate expenditure. Okay. Aggregate expenditure here, in our model, we have no government spending. Oops, sorry. And we have a closed economy. So that X minus M is equal to 0. So if we have no government spending and we have a closed economy, then what does our C plus I plus G plus X minus M equation become? Y is equal to C plus I. So this is really, as I said, our Y is equal to C plus I plus G plus X minus M, right? We talked about that on Tuesday. However, G is 0, X is 0, M is 0, and so what's aggregate expenditure? Y is equal to C plus I. So in other words, when we have output, there's really only two things you can do with the output. You can consume it or you can invest it. All right? Hopefully that's pretty straightforward. Now, here's the third assumption, and this is really where a lot of the new work is done in the model. We have to think about how capital evolves over time. In the last model, we said that capital was fixed, it doesn't change, but now we have to think about how capital changes over time. And so we're going to make the following assumption. What's capital next period? It's just equal to this. All right. Now, this is actually pretty intuitive, right? I think that there's nothing too shocking going on here. What's capital next period, right? What's capital next period? Capital next period is equal to capital this period plus investment. So what is capital going to be next period? It's going to be whatever capital is this period plus the amount we spend on investment. However, there's also something that reduces capital, and that's depreciation. And so D bar here is the depreciation rate. And we are going to assume, once again, that this is exogenous, right? So we're not going to explain where depreciation comes from. We're just going to say that a certain fraction of our capital wears out every period. So once again, what do we have going on here? Capital next period is equal to capital this period plus investment, but then we subtract out depreciation. So there's a force here that increases capital, and that is investment. And then there's a force here that decreases capital, and that's depreciation. All right, make sense? Yeah, I don't think it's rocket science, right? Now, we can also rewrite this equation in a different way. And this is the way we will usually write it. Oops, let me write it like this. If we move this first KT over here on this side, oops. Right. Shoot, there's some. Sometimes it seems so clunky. There we go. Okay. We can also rewrite this equation in this way. When we put the change in KT on the left-hand side, and what's the change in capital? It's equal to the amount of investment minus the amount of depreciation. Okay. So this is our capital evolution equation. What's the key thing here to understand though? The key thing to understand about this is notice that this is dynamic, right? And what do we mean by dynamic? That it's incorporating capital at two different periods of time, right? So it's talking about how capital evolves over time. So now capital isn't just at one point in time, we're actually thinking about how capital moves over time. So really in many ways, this equation is what makes the Solow model, right? Now we're able to think about how capital moves over time. Okay, let's make just a couple of last little assumptions that really make our life easier. We're going to assume that labor is exogenous, right? Let's just use L, let's just make L equal to L bar. Do we need this assumption? No. In fact, it's pretty easy not to use this assumption. It's pretty easy to add population growth to this model, but we're just going to try to keep things as simple as possible, right? So while adding population growth to this model is very doable, let's just keep it as simple as possible, and let's just say that we don't have population growth, labor is pretty much fixed, right? And then the last assumption, once again, to keep things simple, is let's assume that people save and consume a constant fraction of their income. So we're going to assume, oops. What is savings? Savings is just a constant fraction of income. And what is consumption? The rest of it. Okay. S bar here then is exogenous. And S bar here is the exogenous savings rate. So we're not assuming, we're not trying to explain why people save or how much people save. We're just saying people have a savings rate. This is what it is, right? So if S bar is 0.2, that means that people save 20% of their income and they spend 80%. If S bar is 0.5, it means they spend half, they save half, okay? Now, one last thing here. If there's a savings rate, where does all this money that's saved go? Well, remember, there's only two things you can do with your money. You can either consume it or you can invest it. So if you're not consuming it, you're saving it. Where does all the savings have to go? Into investment, right? So in this model, it has to be true that savings is equal to investment. Okay? Because there's only two things you can do with your money. You either consume it or you invest it. So if people don't consume it and decide to save, that money is going to have to turn into investment. Okay? So in this model, the savings rate is also, you could think of this as the investment rate. Okay, that's the model, right? That's the model. That's the major assumptions of the model. So just to be clear here, let's go back and just review what variables are endogenous and what variables are exogenous. Which variables are exogenous? Well, those are probably the easiest ones because they're the ones that have the little bar over it, right? So we assumed labor was exogenous, total factor productivity was exogenous, the savings rate was exogenous, and the depreciation rate is exogenous. One other variable that we will occasionally use is we can also assume in this model that the initial level of capital is exogenous. You kind of have to have a place to start. And so you can kind of think about that initial level of capital as also being exogenous, right? What happens before the model starts, that's going to be given to us. What then are the things that we're going to be solving for? We're going to be solving for output in every period, in capital in every period, in consumption in every period, investment in every period, saving in every period, right? Those are the models that are endogenous. Okay, everybody with me so far? Okay, so it's, really, I mean, once again, the Solow model, there's a reason why it's hung around as kind of a workhorse model for so long, is it really is a pretty simple model. And in many ways, when you think about solving the model, the solution to the model is very simple, right? Very simple. We know that right? Well, now we can rewrite this in this way. What is IT? It's really this, right? So we can plug in for investment and say that investment is just a share of output. Or once again, what's output? These two equations are the Solow model. Right? We have essentially what we'll call the Solow equation, and then we have the production function. Okay. And it's these two equations that really are all of the Solow model, right? If we understand these two equations, we understand the Solow model. So let's think about what's going on here. Maybe the easiest way to kind of understand these equations is to do a graph. Okay. Just do it this way. Okay, so let's kind of do a graph or think about the Solow equation visually. Okay, so here's our graph of the Solow equation visually. Down here on this axis, let's put K. And up on this axis, we're going to put Y, right? So if we can swing back to our Solow equation here, notice that this equation has two components. the investment component, and then kind of the depreciation component. What do each part of these equation look like? Well, what does S bar times Y look like? Well, we know what Y looks like. It's a production function, right? That's what YT looks like. We talked about this yesterday because of diminishing marginal returns. If you increase capital, what happens to output? It goes up, but it goes up, but at a diminishing rate, right? So having more capital increases output, but it increases output at a diminishing rate. This is diminishing marginal returns. So what does S bar times Y look like? It looks just like the output or the total production function. It's just shifted down by a constant amount. Okay, so this is the first part of the Solow equation. It's just our production function, but it's shifted down here to reflect the fact that we multiply it by S bar. What does the second part of the Solow equation look like? Well, this is the D bar times K, right? This is the depreciation. Well, this one is pretty simple too. In fact, I'm going to erase this first production function so we can see this a little bit more clearly. So D bar is just a constant, it's exogenous. So what's D bar times K? It's just a straight line. So now we've graphed the Solow equation, right? Now we've made a graph of this. Now you've all taken enough economics to know that whenever you have a graph and there's two lines and those two lines intersect, something's happening, right? So what's happening here? What's happening at this point where these two lines intersect? We'll call that level of capital K star. What's happening at K star? We'll go back to our equation. What's got to be true about this equation at K star? This part is equal to that part. In other words, capital stock is not growing. It's constant. It's what we call at a steady state. We'll refer to the K star as the steady state level of capital. Once we get to this level of capital, the capital stock stays steady. It's not growing, it's not shrinking. It's just at a constant rate. So this is an important point here, right? That when we get to this point, capital stock doesn't grow. Now, just as important, it's to think about what happens if we're at a level of capital that's lower than the steady state. What happens if we're down here? We'll call this point A, right? What happens if we're at a level of capital that's lower than the steady state? Well, notice what's true at KA. Investment is greater than depreciation. So going back to our equation, if investment is greater than depreciation, what has to be true about delta K? delta K has to be greater than 0, right? In other words, if we're below the steady state, the capital stock is growing. And as a result, output is also growing. However, what happens over time here? This is where I think there's, the solo model is different from the static models that you're used to. What typically has happened in a static model when you're out of equilibrium, right? Well, what happens in a static model is you immediately jump back to equilibrium, right? But that's not what happens here. And the reason is that it can't happen. You just can't accumulate enough capital to jump back to the steady state because you have to save and invest to get to that capital. So you don't just jump back to the steady state in one fell swoop. What happens is you transition path back to the steady state. So what's going to happen next period is you're going to move up here. And then what's going to happen? Capital stock will move in this direction. In every period, we will continue to grow towards the steady state, but we won't just jump there in one period. And once again, the reason we don't jump there is because you have to save and invest to get there, right? We can't just starve everybody for 1 year and accumulate all the capital we need to get back to the steady state. You have to basically accumulate it over time. That's what our capital accumulation equation says. So in other words, what happens is over time, capital and output rise. As we move towards the steady state. But notice something else happens here as we move toward the steady state. What's happening to the rate that we grow? Well, notice down here at the beginning, the change in capital is basically the difference between these two lines. So at the beginning, the difference was quite big. But then what happens to the difference between these lines as we go along? They're getting smaller and smaller and smaller. So in other words, delta K is getting closer to 0 and growth is shrinking. So as we get closer to the steady state, growth shrinks. It gets smaller. It gets closer to 0. Why? What's the intuition here? It's one thing to show you the graph and say, well, those lines are getting closer together. But what's the intuition? Why is growth shrinking over time? Anybody? You get a gold star. Well, if these two, but what happens if our production function, I'm just going to put this on top. What if our production function was just a straight line like this? Would we ever have a steady state? No. Why is our production function look like this with a curved line instead of look like that with a straight line? Come on, Ben, I know you know this one. I made you repeat this 1,000 times last year in China.
Diminishing marginal returns, right?
Diminishing marginal returns, right? Diminishing marginal returns. That's why this curve slopes downward. Diminishing marginal returns. What happens as we get richer and richer? As we get richer and richer, how much output do we get from additional units of capital? Smaller and smaller amounts. And so what basically happens over time is that as we get richer and richer, growth slows because we're getting smaller and smaller changes in output from adding capital. In fact, eventually when we get to the steady state, growth slows to zero, right? So eventually, we get to the steady state and growth goes back to zero, right? So in the Solow model, we essentially have what we could call a transition path, right? I could call this part the transition path part, where we transition to the new steady state. And what happens when we get to the steady state? When we get to the steady state, growth goes to zero and we stop growing, right? And we just stay there forever until something knocks us out, right? Until something knocks us out of the steady state. So the Solow model is a simple model, but you'll see it's a lot, in many ways, the intuition is a lot more complicated because it's a dynamic model. It's asking us to think about how the economy changes over time. So instead of other models that you've seen, static models, in which if you're out of equilibrium, you just jump right back to equilibrium. Really what we have in this model is you have to think about in this model, we have a series of short run equilibriums and then a long run equilibrium. The long run equilibrium is the steady state. The short run equilibrium is the transition path, right? It's the way that we move period by period toward the steady state. And so, this is why thinking dynamically can be challenging, right? Because quite honestly, you think about static models, right? We're used to thinking about economics in terms of static models like supply and demand, right? Really, that's kind of like thinking about things in 2 dimensions, right? So it's kind of like a 2-dimensional graph. What we're really asking you now, when we ask you to think about the world in dynamic terms, is we're really asking you to think in 3 dimensions. And that's hard, right? Because we're not quite used to it, right? We're more used to thinking about things in 2 dimensions and kind of holding time fixed. Now we got to think about things in 3 dimensions, thinking about how the economy changes over time. And what that introduces here in this model is a difference between kind of the short run equilibrium, right, where we move period by period, and then the long run equilibrium, meaning where we are transitioning to, right? And so that's kind of the mechanics of the Solow model, right? And they're quite involved, right? They're quite involved. Luckily, we're going to get some practice here today working on this. Let's do kind of the opposite approach, or take the opposite case. This thing is sorry. Okay. What if, for some reason, capital was greater than the steady state? We had a capital level that was greater than the steady state. So let's think about another example here. So here's our model where we're at the steady state, but for whatever reason, and we'll actually kind of talk about some reasons why this might happen, we are above the steady state. Okay, what's going to happen here? Well, now notice what's going to happen. Our capital stock is going to have to shrink. And how does it shrink? Well, notice that depreciation is greater than investment. At this level of capital, depreciation is greater than investment. So what's going to be true? The capital stock is going to shrink over time. Depreciation is greater than investment, so the capital stock's going to shrink. Also, output will shrink. And so we have negative growth. Do we in one period jump all the way down to the steady state? No. Once again, we don't go all the way down to the steady state because it's going to take a period of time for our depreciation to kind of wear out our capital enough to get us back down to the steady state. So what happens is, period by period, we transition back towards this new lower steady state, right? So we transition toward K star. Notice here, as we get closer to the steady state, our growth gets closer to zero. So it's still negative, but it becomes less negative. Okay, it becomes less negative as we move in this direction. And then finally, what happens at the end? Eventually, K is equal to K star. We're at the steady state. And growth is equal to zero again, right? So eventually we move back towards that steady state. So once again, we get these transitional dynamics. We get these transitional dynamics. That takes place over different periods. All right, so once again, really what this Solow model is asking us to do is think about things in 3 dimensions, right? It's now asking us to explicitly incorporate time within our model. The nice thing about this is now we not only think about what happens to levels of output, but we also can think about what happens to growth. And as we're going to see in a couple of minutes after break, this then really changes how we think about why rich countries are rich and poor countries are poor, right? The Solow model gives us some more deeper insight into why rich countries are rich and poor countries are poor. Before we get into kind of the implications of the Solow model, I've kind of worked through an example using the Solow model in terms of a graph, right, and kind of intuition. But now let's work through a numerical example of the Solow model. So while we've done this graphically, let's see if we can do this numerically. So here I'm going to give you some values. Let's say that L bar is equal to 1. We're going to keep this very simple. A bar is equal to 1. The depreciation rate is 0.1. The savings rate is 0.3. And let's say that our initial level of capital is 2. Okay, so our first question here is, what's the steady state level of capital? Okay, well, what's true when we're at the steady state? When we're at the steady state, we know that the change in capital has to be equal to 0. In other words, that has to be true. Okay? So let's plug in. What's S bar? 0.3. What's Y? Y is, remember, that, but A bar is equal to 1 and L bar is equal to 1. And so what we really get here is k to the 1/3 minus that. So we're trying to solve for the capital stock that makes this true, right? We're trying to solve for the capital stock that makes this true. So we can put KT, the one part of KT over here on this side. Okay. Let's multiply each side by k to the negative 1/3 power. So that this cancels out. And we have 0.1 times k to the 2/3 power, right? Because k to the 1/3 plus k to the 1 is just k to the 2/3 power. Divide each side by 0.1. K to the 2/3 power is equal to 3. Take each side to the 3/2 power. And what do we get? What's k? What's 3 to the 3/2 power or 3 to the 1.5 power? It's 5.19. That's the steady state level of capital. Everybody see what I did there? Right? So basically, going back through this, I just took what I knew to be true at the steady state, which is delta K is equal to 0, meaning S times Y minus D times K has to be equal to 0. Substitute what I know, use a little bit of algebra, and I find that the steady state level of capital is 5.19. What's the steady state level of output? Well, that's pretty simple too. Just plug it into our production function, right? A bar is equal to 1 and L bar is equal to 1. So this is 5.19 to the 1/3 power. Or Y star is equal to 1.73. That's the steady state level of output. Okay. Let's do one more question. Notice that we're told at the beginning that K, the initial level of capital is 2. So what then is going to be the change in capital the next 2 periods? So what do we have to do here? Well, we have to go back and use our capital accumulation equation. Okay, what are we trying to solve for? Delta K1. What do we know? S bar is 0.3. Here, let me back up here and put in a couple of steps. So what we can do here to solve this equation is we can essentially put in the initial level of capital into this equation, right? So what's S bar? 0.3. What's the initial level of capital? 2. D bar is 0.1. The initial level of capital is 2. And we can solve for how big of change this level of capital is if we start at a capital stock of 2. I won't ask you to break out your calculators, but what you will find is that the change in capital is 0.178. So in other words, the capital stock's going to go up. Does this answer make sense? I see some tentative nods, right? So let me tell you, when you're taking an exam or you're doing a homework problem, it's one thing to get a wrong answer. It's another thing to get a wrong answer that doesn't make any sense, right? So when you do problems like this, math errors are going to occur. Sometimes you'll get something screwed up. What I'm looking for when you screw something up is, quite honestly, for you to say, hey, this answer looks wrong to me because it doesn't match my intuition. right? So whenever you have a problem like this, you need to be asking yourself, does this answer make sense, right? Regardless of whether it's right or wrong, does it make sense, or can I say that this has to be wrong? So let's think about this. Does this answer make sense? We might be able to think about this using our Solow diagram. Where did we find the steady state level of capital was? There. Where is our initial level of capital? There. So what needs to be true about the change in capital? It has to be positive, right? If we don't find that it's positive, we know that we screwed something up. And so the fact that it's positive here makes sense. So basically where we're going in the next period is we're going from 2 to 2.178, right? This is growing by 0.78. What's going to be the change in capital in the second block? Well, now we want to use this, the capital stock now in the first period, which is 2.178 in our equation. So just as we did before, we want to calculate this equation, but notice now instead of using K0, we want to use K1. What's K1? 2.178. Okay. Here we get an answer of 0.171. Now, does this answer make sense? Yes, because notice here, not only is it positive, but notice what happened to the size of the change in K2 relative to the size of the change in K1. It's smaller, right? Notice that the change in capital stock in the second period is smaller than the change in the first period. What's happening to growth? It's slowing as we get closer to the steady state. That makes sense to us. If we would have got a bigger number, we would know that doesn't make sense, right? Because a bigger number means that growth is speeding up as we get closer to the steady state. So the fact that we have a positive number there, but a smaller number, makes a lot of sense, right? Makes a lot of sense. So that's kind of thinking about working through the mechanics of the Solow model, both graphically, right, or kind of more intuitively, and then thinking about working through it more numerically, right? You'll have to do examples of each of these on homework number 2, right? So I'm going to give you some problems of working with the Solow model graphically, and then also at least one question where I ask you to kind of work through the model numerically. And so I think that what I've done here should be useful practice for you, right, in doing this for yourself on the homework. All right, this seems like a good time to take a break, okay? So let's maybe take a 10-minute break, right? So maybe at 10:10, we'll come back and we will talk about what all of this means, all right? And I'll leave Zoom up and running if any of you want to chit-chat with each other, all right? So I'll see you at 10:10.
Hey, Mr. New,
Yeah.
quick question.
Sure.
So I did my number 6 with unemployment. I just thought you wanted us to compare the two.
Mm-hmm.
So then I went on the Fred and found the unemployment for the same time, and then just detrended them both and did that. So I was wondering, could we have an extension? Because I don't have any time really between lunch and time to fix it.
You can just send me what you have, Cole, and I'll grade what you
Okay.
have. I'll grade the question as you answered it. Okay.
Yep.
Okay. Cool. All right, everybody. So I was trying to think about, I mean, this whole thing about teaching and learning online is just a very weird thing, right? Not actually being able to talk with people, or there's something about the whole online teaching experience that almost, I mean, not only does it kind of take the fun out of sometimes of learning, but it actually makes you want to have less fun, right? You're kind of, you feel, at least I feel this in myself, I feel like this thing like, well, let's just get it done, right? Let's just go, 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 go. And the sooner we can get off Zoom, the better. And so, yeah, it's difficult. So I was trying to think about how can we interact more here. And I won't claim that this is a great solution, but I thought, well, you know what we should do is what we do around the dinner table sometimes. So uh, sometimes when we're sitting down to eat, we have this little card game where you pull these cards out, and they basically have, you know, like either questions for discussion, or we also have a card game called Which Would You Choose? All right. So I thought, just to break up class just for a couple of minutes, I'm going to pick a card for family discussion, because we are a family this block. And I'm going to put you in the breakout rooms. I'm going to put you in 2 breakout rooms and give you about 5 minutes to talk about this as a way to kind of just interact with each other. And then we can kind of come back. And if you want to play another one, we can play Which Would You Choose for another couple of minutes. Okay, so I am randomly picking into my little card thing. And here's what I'm picking out. If you were an ice cream flavor, what would you be? And what about the person to your left? Okay. So I'm going to put you in 2 breakout rooms. I'll put you in 3 breakout rooms, right? Put you 3 breakout rooms. Chat amongst yourself about, if you were an ice cream flavor, what would you be? And what about the person to your left? All right. So do this for a couple of minutes, and then I'll pull you back, and hopefully we'll have fun.
was what my favorite is. And that's, those the birthday cake ice cream that you can get at some places. Love that stuff. And I don't know. Maybe if I really want to make it psychological, right? And Ben said that I'm kind of like vanilla because everything's plain around me. And sometimes that stuff looks plain, but then you have it's still special, right? So you go. And Ben is on my left on my screen. So let's see. Let's see. But that's a tough one. Give me a few minutes. If someone wants to go, we can get back to me, and I'll think about what that should be.
Hey Todd, what do you think my choice of myself was for ice cream flavor? What do you think?
Okay, I'm gonna go out on a limb. I'm gonna say, Ben, you're green tea ice cream.
Green tea, disgusting.
Sorry. Some people actually like that.
Yeah, it's weird.
But it's an unusual flavor. It's an unusual flavor.
You could have at least picked a better tea, Todd.
But you don't like those little mochi things, little mochi green tea? Yeah, I mean, now that I say it, I don't really like those things either, but so I missed what was Rose, what was your flavor?
It was one of the flavors that I used to work at Baskin Robbins. So wow. I chose one of their flavors, which was a vanilla base with a black raspberry ribbon and cashews, because it's my favorite. Very
impressive. Yeah.
Yeah, it's no big deal. I'm an ice cream expert, so.
That's kind of like a dream job.
Mm-hmm. Especially in Texas.
Do you really get to eat as much as you want?
Yes.
That would be very dangerous.
I do.
I probably just have with diabetes.
Yeah.
Yeah, that's cool. And Jin, are you here? I don't know if you're in Jiaoyan. They might just be recording this. So they're both in China, so they're having a hard time. Wow.
No, I'm here.
Oh, are you here? Okay.
Hi. Well, actually, my favorite flavor is coffee. Because there's a flavor of coffee. Because I love Häagen-Dazs, so there's a flavor of coffee, and I really like that.
Strong choice.
Yeah.
But just coffee, or you got to have like a little chocolate in that too, right? Like mocha, or you just
I love chocolate as well. Yeah.
Strong choice. Very, very well done. All right, we should probably go back. So I'm going to leave the room and pull you guys back. Oh, sorry, I forgot about the 60-minute delay. Or not 60 minutes, sorry, that would suck, 60 seconds. Okay, I think everybody's back. Cole, are you actually eating ice cream? Okay. I thought maybe that our discussion actually inspired you to
no, if I had it, I'd try it, but I found out this summer I'm lactose, so it kind of ended my ice cream days.
That is the weird thing about taking class at home is like, for me, my kitchen is kind of right over here. It's like a little tempting not to run over there and just kind of keep on eating all day. So, all right. How about we'll save which would you choose, or which would you choose question for this afternoon, right? So let's talk here a little bit about the implications of the Solow model, right? So we've talked about the kind of the mechanics of the Solow model, the intuition, but now we want to talk about what this really tells us about the important question of why are rich countries rich, poor countries poor, and why do we have differences in income levels? Okay, so, right. So you can show in the steady state that this is true. That per capita output, which remember is output divided by population in the steady state, is equal to this. Is equal to this formula. How do you get this? You just set delta K equal to 0, right? And solve for the steady state level of capital, just like we did numerically a couple of minutes ago. And then once you have the steady state level of capital, you plug that into your production function to get the steady state level of output. You divide that by L, and you get the steady state level of per capita output. All right, so I'm not going to go through all that algebra, but it's really the algebra that we did before, except instead of using numbers, you're just going to be using symbols, okay? Well, let's do what we did yesterday. Let's fit this to countries. Sorry, my dog hates the postman. All right. Okay. So let's fit this to the 5 richest and 5 poorest countries. So just like we did yesterday, we can think about this calculating this equation, right? So if we know that this is true, right? This first equation is true from the Solow model. So let's then think about calculating this as a ratio. The income level of the 5 richest to the 5 poorest should be the ratio of A in the rich countries relative to the ratio of A in the poor countries to the 3/2 power. And then the ratio of S savings to depreciation in the rich countries relative to the ratio of savings and depreciation in the poor countries to the 1/2 power. We have data on output, right? So we have data on this. We have data on S, right, across countries. We know what their savings rate is. We don't have data on depreciation. Well, let's just assume that this is equal to 0.1 for all countries. So let's just assume that there is no variation in depreciation across countries. This is probably not a horrible assumption. And then, given we have data on this and this, then we can kind of calculate the implied importance of A. Okay, we can calculate the implied importance of A. So, just like we did yesterday, what's the ratio of income in the 5 richest to the 5 poorest countries? This is 64. The 5 richest countries are 64 times richer than the 5 poorest countries. What is the ratio, what is this ratio over here on the right of the savings to depreciation in the 2 countries to the 1/2 power? Notice this is kind of a surprisingly low number, 2. In other words, how much of the variation in income is being explained by variation in savings rates across countries? Very, very little, right? There's very little differences in savings rates across countries. So what does this mean? What accounts for most of the differences in incomes across countries? A. A is accounting for about 90% of income differences. According to the Solow model. 90%. 90% of differences is accounted by A. If you remember yesterday in the simple model, we found that A accounted for only about 75% of the differences. Now we find that A accounts for 90% of the differences. Why? Well, the reason is two reasons. The fact that this is a dynamic model actually makes capital less important because of diminishing marginal returns, right? It's diminishing marginal returns that keeps capital less important. That's one of the reasons why capital becomes less important in the Solow model. The other reason is the fact that it's dynamic makes A more important, because when you have an increase in A, that also increases your incentives to invest in capital, right? So in the dynamic model, something that we did not have in the simple model yesterday, when A goes up, it actually gives you more incentive to invest in capital. So you accumulate more capital, which actually increases the importance of A, okay? So A only becomes more and more important in the Solow model. So really, in many ways, re-emphasizing the point that we made yesterday, that when we think about differences in income across countries, we really have to understand A, total productivity. If we don't understand A, we're not really understanding very much about what's going on. And so that's one way to think about this, but I guess the other way of thinking about this is you really can't think about differences in income levels as being related or primarily related to differences in capital. And this is one of the reasons why the Solow model has been, particularly when it was first introduced in the 1950s, was such a radical departure in economics. Because prior to the 1930s, 1940s, 1950s, there was this idea that, well, countries are poor because they don't have enough capital. And if somehow we gave them enough capital, they would just become richer. And so that was, in many ways, the development strategy of the 50s and 60s in many, many less developed countries is, let's just build roads, build bridges, give them a lot of capital, and they'll become rich. And how did that work out? Pretty much a disaster. And the Solow model tells us why, is that capital is actually a pretty small fraction of what makes a rich country rich. Much more of it is productivity. And that is a much more difficult thing to increase within countries, right? It largely goes back to what we talked about yesterday, human capital and institutions. And so it would be great. It actually would, the world would be an easier place for us economists if capital was more important in explaining income differences, because capital is something that it's more obvious how you increase. The problem is capital is really not a big, doesn't play a huge role in why rich countries are rich and poor countries are poor, right? It's more of a secondary role. The important stuff is productivity, and that's a lot harder to try to increase because where productivity comes from is a lot more complicated. And that, of course, is where we're going to turn a little bit this afternoon and tomorrow when we move into chapter 6, where we're going to try to think a little bit more clearly about where productivity comes over time. But yeah, you know, if you think about this, and I'm going to reemphasize this afternoon, so I won't talk about this too much. But if you think about things in your own life, you really kind of see how capital plays a relatively small portion, but productivity plays the largest portion in increasing standards of living. Just one example that always jumps out to me, there's thousands of examples, but one example that I always find kind of interesting is that since 1980, Wisconsin cows produce 2.5 times more milk than they did. Right? Think about that. Since 1980, so today, a Wisconsin cow produces 2.5 times more milk than it did in 1980. Right? That can't be because of capital. The cow is largely the same thing. I mean, of course, there's been some genetic improvements, but that's, you know, that also accounts to technology, right? I mean, something else is going on here to explain how we're getting so much more milk out of cows. And that is that this amorphous thing of productivity, right? Lots of little steps that increase production, lots of little improvements in how we put things together. And so, you know, as I said, that's where most growth comes from. And that's really what the Solow model is telling us, right? Is that really productivity is what's driving income and growth. And relatively little can be explained by capital. Let's do a couple of other examples in kind of using the Solow model, just to make sure that we understand all of its implications. Okay, so let's work through a couple of examples here, and I'm going to focus kind of on numerical, intuitive examples, just to make sure that, as I said, we kind of understand the basics. Let's think about an increase in the savings rate. S-bar. How does that impact output growth in the Solow model? And here we have to think about what's the impact in the short run, but also what's going to be the impact in the long run. Okay. So we have an increase in the savings rate. How do we graph this? Well, it's got to be an increase in S-bar, right? An increase in S-bar is going to shift our production function. Apologize. It's not going to be the nicest looking graph. It's going to shift our production function in this way, and notice that it moves us to a new steady state. So now we have a new steady state. Does that mean that we immediately jump from this steady state to that steady state? The new one? No, we have to transition path over time. So what's going to happen now is now we're below our new steady state. We are going to have to evolve over time and move in this direction. In other words, in the short run, Because now capital is less than our new steady state, we're going to have positive growth in capital and we're going to have growth. However, growth will slow as we get closer to our new steady state. And what happens in the long run? Growth goes back to zero. But output and capital, the level of output and capital are higher than they were before. We're richer. Okay. So let me say this again, because I think this is a really important distinction to make. If we save more, what happens to growth? It goes up in the short run, but not in the long run, right? If we save more, yes, we're going to grow faster in the long run. I'm sorry, we're going to grow faster in the short run, but we're not going to grow faster in the long run. We're going to go back to zero growth. However, we will be richer in the long run. We'll be richer in the short run and we'll be much richer in the long run. So here what we see is that really saving more doesn't make you grow faster in the long run. It's only going to cause you to grow faster in the short run. So in other words, to kind of visualize what's going on here, if we drew another graph in which we put time here and output, you could think about what's happening to output. Initially, output is constant. And then there's a change in the savings rate. And what happens when the savings rate changes? We grow faster in the short run, but in the long run, we go back to no growth. But output is at a higher level than it was before. Okay. So that's really what's happening. And the graph of capital looks the exact same, right? The capital is flat, and then we have a change in savings. So for a short period of time, we grow faster, but in the long run, we go back to zero growth. We're just richer than we were before. So will growth cause you to be richer in the long run? Yeah, or I'm sorry, will savings cause you to be richer in the long run? Yes, but it won't necessarily cause you to grow faster. Why? Diminishing marginal returns, right? Diminishing marginal returns. That's the reason why just accumulating capital is not going to lead to growth in the long run. Yes, it will make you somewhat richer, but it's not going to lead you to grow in the long run, right? It's not going to lead you to grow in the long run. So, once again, it all comes, the relative lack of importance in capital all comes down to the fact that diminishing marginal returns plays such a big role in this model. Let's think about another example. Help us kind of use Solow model. Let's talk about a natural disaster. And a one-time decrease in capital. Okay. Okay, so here's, once again, we always start kind of in the steady state. And now there's a natural disaster, let's say a derecho, right? A derecho comes, crashes through our economy or through our country and reduces capital. Now, what's happened here? Has this changed our steady state? No. This is a one-time event, right? It hasn't changed our savings rate. It hasn't changed our depreciation rate. It's just meant we have less capital. So I think the best way to think about this is what happens is we just get knocked down here below our steady state. But the steady state itself has not changed, right? The steady state itself has not changed. So then what happens? In the short run, and this seems kind of counterintuitive, but maybe it's not if you think about it more carefully, we grow faster, right? In the long run, though, growth goes back to zero, and we go back to initial level of capital and output, right? So in other words, we grow faster initially, and then what happens over time? Growth slows as we get back to the steady state. This seems maybe a bit counterintuitive. However, I don't think it is. You know, for instance, I haven't seen the latest economic reports in Iowa, but strangely enough, the derecho in Iowa is probably some sort of economic stimulus, right? Why? Well, it's a stimulus because what had to happen after the derecho? People had to have their roofs put back on, their houses repaired, trees cut down. It was a stimulus in spending, right? So while the level of output might have got knocked down, it's actually going to, in a strange way, increase growth. We see this similar phenomena happen after wars, right? Where strangely wars can reduce the level of output, but actually stimulate economic growth once the war is over as economies try to recover, right? And so, yeah, so it's kind of unusual, or maybe I shouldn't say unusual, but kind of counterintuitive. Let's just talk about one more example. I hate to run a little bit over, but I want to get everything in today. One more example. Let's talk about a one-time increase in population. What happens if we have a one-time increase in population here? Okay. Well, if we have a one-time increase in population, what's going to happen? That's actually going to increase our amount of output, right? Because one of the factors in our level of output is population, right? So we should actually see this go up. And so having more people should actually increase our output in the long run and in the short run. And in the short run, growth goes up. In the long run, it's not impacted. That's kind of the simple answer, right? That having more people allows you to produce more. So, in this example, and remember here, just to be clear, this is a one-time increase in population. So, I guess a more specific example would be, let's assume that nobody shows up at the border, the southern border of the United States, and a whole bunch of people run across the border one day and then they close it, right? That actually is going to increase overall output because we have more people. Of course, that's not really what people argue about when they talk about immigration, right? I don't think anybody argues that immigration reduces the level of output. What many people are worried about is what happens to per capita output, right? Does the increase in output offset or accommodate the increase in the number of people so that the output per person stays the same? And in this model, the answer is no. Per capita GDP output actually falls in this model. Why? Diminishing marginal returns to labor. So when you have an increase in the population, yes, it's going to increase the size of the pie. But diminishing marginal return says that the pie won't increase enough to keep everyone's slice the same. Right? So in other words, when you have people come, they're going to increase the amount of output. But what's the problem? Diminishing marginal returns to labor. The new people who come are not going to be as productive as the people who are already here in this model, right? I want to emphasize in this model. In this model where labor is labor, where people are people, right? We have no distinction between different types of people. In this model, the people who come are going to be less productive than the people who are already here, meaning that the pie will go up, but not enough to keep everybody's slice the same. So the pie is going to be bigger, but because you have to divvy it up between more people, each individual slice is going to be smaller. And so this is really, in many ways, at the heart of the argument against immigration, right? We could call this a Malthusian result. And Thomas Malthus, you might remember Malthus, we talked about him in Principles of Macro. Malthus was a big believer that the world was going to crash and burn because population gets too big. And as population gets bigger and bigger, there's no way that we can feed all these people because of diminishing marginal returns. So Malthus's prediction was as population gets bigger, diminishing marginal returns mean that standards of living will get smaller and smaller until eventually we fall to a point where people start to starve. And people starving is a sad thing, of course, but that's also a good thing because it means there's less people so we can have higher standards of living, right? So Malthus was, very much a pessimist about the future of economic growth and very much a pessimist about population. Of course, does that Malthusian view of population really jibe with what we've observed in the real world? And the answer is no. As our population has gotten bigger, we've gotten richer. And so, that's a real reason to kind of question not only Malthus's thinking about population, but also the Solow model's thinking about population, right? Because we have not seen what the Solow model says, that an increase in population should actually reduce the per capita level of output. There's probably some things that the Solow model is missing. And that's kind of going to be one of the things we talk about this afternoon, right? What exactly is the Solow model missing here? But I I think it is important to talk about this because for many people who have a real pessimism about population growth or about immigration, they really think about the world in very Malthusian terms, right? That there's no way that if we add more people, we can possibly produce enough to prevent per capita levels of income from falling. Despite lots of evidence to the contrary, they believe that it's hard for us to maintain per capita levels of income with more people. So anyway, we'll kind of come back and talk about this a little bit later. And we'll talk more detail about why we should maybe question how Malthus thinks about the world, how we should maybe question the result from the Solon model, and maybe also question, pessimists about immigration. But that's probably getting a little bit ahead of ourselves. Okay, sorry for taking a couple extra minutes here. We will meet back here at 12:30. What I want to do at 12:30 is finish up a couple of things on chapter 5, and then that shouldn't take very long. And then I also want to just begin to talk a little bit about chapter 6 and do kind of some introductory conversation about where we're going to go tomorrow. So we'll do that at 12:30. Remember to turn in homework number 1. I technically you need to turn it in by 1 o'clock, but turn it in this afternoon. Okay. All right. Thank you very much for your attention. We'll see you in a couple hours. All right. See y'all.
We submit it by email, right?
Submit it by email, please.
Yeah, okay.